We have a very interesting question here from the 2022 CAPE Applied Maths Unit 2 exam. So it says two particles of mass 12 kilograms and 8 kilograms. You see I have them drawn here. So this is our 12 kilogram particle and our 8 kilogram particle. They are connected by a light inextensible string. So this here is a string. I have it as rope. Maybe I should change it to string, which passes over a fixed, smooth, weightless pulley. Both particles are initially held at the same horizontal level, 100 meters above the ground. So we have our ground here. Let's call this ground. And we are saying that we are 100 meters above the ground. So it's 100 meters above the ground with the string taut. So that just means it's pulled tightly. And the particles are then released to move freely under gravity. First thing they want us to do is to determine the acceleration of the system. So in this pulley system, we have a particle that is 12 kilograms and one that is 8 kilograms. Now, one of the things I want to assume is if you're looking at this, you would realize if we was to release this, you would find that the heavier side is where the whole system would try to move. So just imagine us releasing this and you will start to see it falling this way. Therefore, I just want to say that if I'm going clockwise in motion, we're going to consider that to be a positive value. And if we're going anti-clockwise in motion, we'll call that a minus. We know that when gravity acts on this particle, it will create a force pulling it down towards the ground. We know that force can be calculated by mass times acceleration. So in this case, the acceleration would be acceleration due to gravity. And we know that acceleration due to gravity, we'll assume in this case for this subject, is 10 meters per second squared. Therefore, the force as a result of gravity on the 8 kilogram particle would be equal to 8 times 10. This would give us a force of 80 newtons. We have another particle here that has a mass of 12 kilograms. If we apply the same concept to the 12 kilogram particle, we would have 12 times the acceleration due to gravity again, which is going to be 10. Therefore, the force would be 120 newtons. So we know that this force here is 120 newtons. We also know that a string is experiencing a force, and this force is called tension. So tension is being pulled upwards here. We also have a tensile force that would go upwards here. And one thing I should note is that these two T's are the same. That's important to note. What I want to do is come up with an equation for each particle. So we'll start with particle 8 kilograms. And what we'll do, we'll try to find the net force of that particle, which is equal to mass times acceleration of that particular particle. As we said earlier, if we're looking specifically at the 8 kilogram particle, we realize that the tension in this particular particle is pulling it this way. Now, if I follow this motion, similar to what we have here, you realize that it's going clockwise. It's following this direction here. And the 80 newtons, it's almost as if it's going downwards, which is opposing the flow of the clockwise motion. If we try to find all the forces acting on the 8 kilogram particle, we know that that would give us the net force. So since we know that the net force is mass times acceleration, we could say mass times acceleration is equal to this T, the tension, which we said was going clockwise. So that would give us a positive value. And now we have to add that to the force going anti-clockwise, which would be the 80 newtons. So we'll end up with minus 80 newtons. So there are no other forces acting upon this particle. So we can say that we just figured out our formula for the net force of particle 8 kilograms. Now we need to find it for particle 12 kilograms. We also have a net force that is equal to mass times acceleration. So similar to what we did earlier, mass times acceleration would be equal to the sum of the forces. In this case, if you look at the tension acting on this particle, it goes anticlockwise. Therefore, we could say that it's minus T, and when we look at the force as a result of gravity, we will see it's 120 newtons. So this 120 newtons is going in the positive direction. In other words, it's looking like it's going clockwise. Therefore, we would say that this part would be plus 120 newtons. We know that the mass of the particle, that is 12 kilograms, is 12 kilograms. So we can just say that 12 for the M here, A, is equal to minus T plus 120. On this side, we can say the particle is 8, so we could say 8a is equal to t minus 8a. Then we have two equations with two unknowns. The acceleration that we have to find for this question here, and the tension that we have to find for this question here. So I'll do two of them simultaneously. All right, so when I'm looking at this, I can see that I have a negative t and a positive t. So if I was to add these two equations, these t would cancel out and it would only leave me back with a to solve. So let's add these together. So we have 12a plus 8a, which is 20a. T plus negative t would give us 0, and 120 plus negative 80 will give us 40. So if I want to solve for a now, I just need to divide both sides by 20 and I'll get the value of a. So in this case, the acceleration, once the system is released, would be equal to 2 meters per second squared. Now we could find the tension. So now that we have the value of a, we could substitute this into an equation that we have here, either this one or this one. So I'll just use it with the first one. So we'll have the equation 8a is equal to t minus 80. So we'll end up with 8 times 2, I know the 2 is from acceleration here, which is equal to t minus 80. So 8 times 2 is 16, equal to t minus 80. So if I bring the 80 on the next side, I'll add 80 to both sides, I'll end up with 16 plus 80, which is equal to t. Therefore, the tension is equal to 96 newtons. If I try it with the other equation, I'll have the same effect. So I'll have 12 times 2 is equal to negative t plus 120. So 12 times 2 is 24, and that's equal to negative t plus 120. If I bring the 120 over, I'll have 24 minus 120 is equal to negative t. I'll end up with negative 96 is equal to negative t. If I divide both sides by negative 1, I'll end up with t is equal to 96 newtons again. So that's the values for tension and acceleration. Okay, so the next thing what we need to calculate is the distance traveled by each particle after 6 seconds. So what we know is, we know the time, which is 6 seconds. We know the acceleration, which is 2 meters per second squared. We got that from the previous question. And we know it started at rest. The initial speed would have been 0. And what we want to find is the distance traveled, or s. So we have s, u, a, t. Now, if we look at the SUVAT formulas, we want to look at the one that includes U, A, T, and S. So we don't want anything with a V clearly. So we take this out, take that out, this out, this out. So we're left with S, U, A, and T. So we have everything that we need here, right in this formula here. So using the formula, S is what we're trying to find, or the distance they travel. So you end up with U is 0, so that's 0 times T, which is 6, plus half times 2 times 6 squared. So S is equal to 0 plus half of 2 is 1, 6 to the power 2 is 36. S is equal to 36 meters. So both of them travel for a distance of 36 meters. What happens is that 12 kilogram one, since it's the heaviest one, will drop for 36 meters, and this one over here, the 8 kilogram one, would go up 36 meters. Whatever the case is, both of them travel a distance of 36 meters, whether it was up or down. So I'll try to draw a sketch for you to see what that looks like. So as you can see here, we were initially 100 meters from the ground. What happens here is that we move 36 meters down for the 12 kilogram one. So then if we were 100 meters high and we went down 36, that means the new height is 64 meters. Now for the 8 kilogram one, we were initially 100 meters high, but now we add 36 because we went higher. So our new height for this one is 136 meters. So this is just for you to have a general idea of what happened here with the distances. So both particles moved a distance of 36 meters, and this is their relative locations. So even though this is not needed for question 3, this is just to give you an idea of what took place. But this is the distance that each particle moved. Now for our next question, what we need to do is determine the velocity of a 12 kilogram particle just before it hits the ground, if it is disconnected from the string 6 seconds after the system is released. Now, one of the key things we need to realize here is that when we move from here, so before we were here at rest, and after we were here in motion, what you would notice is that we were already starting to move. So when we reach the mark 64 meters above the ground, remember this happened after 6 seconds, we already had a velocity. So our velocity at this point is not at rest. Our velocity just before the string bursts is going to be something. Okay, so we have to work out what that is first. So some things that we want to talk about is that after this 6 seconds, the particle would be subject to gravity, meaning that it's no longer being held back by this 8 kilogram particle, so it would be falling under the influence of gravity. So in that case, the acceleration for this 12 kilogram particle would be 10 meters per second squared. After the 6 seconds, we just identified that it would actually be a distance of 64 meters from the ground. The time, we do not know how long it takes to get from this point to the bottom. We know that there's a velocity that it's starting at, so the initial velocity is something that we need to work out. We need to work out what was the initial velocity. So remember, this particle, while it was coming down, remember before in this case here, it was at rest. Now after the 6 seconds here, it was in motion. So it started from 0 at this point, but by the time it reached down here, 64 meters before touching the ground, it would have had a velocity as a result of the acceleration that we calculated earlier. So just remember that the acceleration that we had at 6 seconds was 2 meters per second squared. And this was as a result of it being held back by this 8 kilogram particle. It had to have a velocity at this point just before release. So we need to figure out what that velocity was. And then afterwards, once we have that, we could then figure out what the final velocity is when it actually smacks the ground. I just want to differentiate between the two accelerations. Now, when this was moving with the particle holding onto it, it was slowing it down. So it was keeping it back. So therefore, it could have only accelerated at 2 meters per second. However, when this string is disconnected or burst, it's released, it's freed, so it can drop as freely as it wants under the influence of gravity, which is why the new acceleration, as soon we cut it, as soon as disconnected, would be equal to 10 meters per second squared. So I just want to show you a little analogy here. This guy is pulling the load. So as you can see here, when this is in equilibrium, and as he releases, it starts to accelerate. Okay, now imagine if this is a load and someone is trying to hold it, the minute that this bursts, if this was to burst, you would start to see this start to drop suddenly. And that's because as soon as it starts to drop, it's under the influence of gravity and no longer being held back by him. Likewise, in our situation here, this 8 kilogram particle was holding back this 12 kilogram to only 2 meters per second. Therefore, we need to figure out what was the velocity at this point when the acceleration was 2 meters per second after it started from rest. So we could say in this scenario, from scenario before to after, just before the disconnection, initial velocity before was 0 meters per second. Okay, the final velocity we do not know yet. We knew the acceleration was equal to 2 meters per second squared. We know that the time was 6 seconds. So then we could figure out what V is. So the Suvat equation that we use in this case is V is equal to U plus AT. So we have U is 0 plus 2 times 6. Therefore, the velocity is 12 meters per second. So right before this is disconnected at this point here, velocity is 12 meters per second. So what this means is that our initial velocity after the disconnection would now be 12 meters per second. So just before it was disconnected, it was already going at 12 meters per second. So what we need to work out now is how fast was it going after it covered 64 meters and after it was under the influence of gravity at 10 meters per second squared. If we go back to the Suvat formula that we used earlier, we realize that the only one that's going to work for this case with what we have is V squared is equal to U squared plus 2 AF. So we don't know what V squared is. That's what we're trying to figure out. But we know U squared is 12 to the power 2 plus 2 times 10. Since we are walking with gravity, we are not opposing gravity. So in this case, gravity will be positive. So 2 times 10 times 64. Then we could say V squared is equal to 144 plus 2 times 10 times 64 is 1280 is equal to 1424. Now in order to find this, we need to find the square root of V. So that means our velocity is equal to 37.74 meters per second. So what that means for this particular question, the moment that this string actually burst, it was moving at 12 meters per second, and it had to fall for the remaining 64 meters here, and by the time it actually reached the floor, it was going at a speed of 37.74 meters per second. And during this time, it was under the influence of gravity, which had an acceleration of 10 meters per second squared. Part B of the question, a ball of mass 6 kilograms is dropped from the top of a cliff, which is 15 meters high. So let's say we have a cliff, and we have the ball at the top of the cliff. So now what we're going to say is the height of this cliff is 15 meters. So we know that the mass of the ball is also 6 kilograms. Alright, so the first thing they want us to do is to calculate the potential energy. And as we know, the course assumes that gravity is 10 meters per second squared. So the question asks, calculate the potential energy of the ball when it has fallen to 5 meters from the top of the cliff. Imagine that this ball actually dropped, and it's dropping 5 meters from the top of the cliff. So it's 5 meters from here. So this is 5 meters. So let's say the ball was right here at 5 meters. That would mean that from where the height is now, it's not going to be 15 meters anymore. It's not going to be 15 meters anymore. It's actually going to be 10 meters from the ground. Now, potential energy is equal to mass times gravity times height. So we're looking at a potential energy when it was 10 meters away from the ground, because we said here is 5 meters from the top of the cliff, there where it has fallen. So now we have mass, which is 6 kilograms, times gravity, which is 10, multiplied by height, which is 10 at this point as well too. So this would give us 600 joules. So that's our answer to the first question. Now for the velocity of the ball when it hits the ground, what I want to obtain is the maximum potential energy. Why do I want a maximum potential energy? Because if I'm able to figure out what the maximum potential energy is when it was at 15 meters high, by the time it hits the ground, I would know what its maximum kinetic energy was, and therefore the maximum velocity reached just before hitting the ground. Now, using the principle of conservation of energy, energy before is equal to the energy after. So the energy before of this ball, we have two different energies that could potentially happen. Potential energy, and we have the kinetic energy. So at this height, we have mgh before plus kinetic energy before as well. Then we'll have potential energy after as well as kinetic energy after. Now at this point, remember, there are two scenarios where they're going to be zero. So at the top of the hill, the ball is not moving. So the velocity at this point is zero. Therefore, this kinetic energy in the beginning is going to be zero. Similarly, when the ball hits the ground, there will be no height. So energy after would be equal to 0. So therefore, we will be left with mass times gravity times height before is equal to the energy half mass velocity squared after. M is 6 times 10 times the 15, which is equal to half times 6 times v squared. So you could basically say that the 6's cancel out, okay? I'll be left with 150 is equal to half times v squared. Now to get rid of a half, I just multiply both sides by 2. So 2 times 150 is 300, which is equal to v squared. Now in order to find v, which is the velocity as soon just before it touches the ground, it's going to be square root 300, which is 17.32 meters per second. The reason why I didn't use the previous energy at this point is because the ball, it has already picked up velocity, so it will also have some form of kinetic energy. So in that case, even though the kinetic energy would be 0 in the beginning stage. By the time it hits 5 meters, you would have potential energy going on. So we have two different energies to consider. This is why I answered the question from the maximum height, it would have given me maximum potential energy, and compared it to where I would have gotten the maximum kinetic energy at the moment just before it hit the ground. Okay, so the next thing we have to do now is prove that in a closed system, the change in the velocity of an object in free fall is independent of its mass. So what this is telling us is that we're looking at this ball. So let's take a little look at this ball. So say we have the same ball here and it's falling in free fall. In a closed system, we're assuming that there's no resistance, there's no opposing force slowing it down from falling. So when it's falling, only has gravity acting upon the ball. We know that some of the forces in the y plane for this ball would be equal to mass times acceleration, or the net force. So we need to figure out what is the net force acting on this ball. So we know that this ball has a mass, okay, and it's falling as a result of gravity. So if we say that ma, which is the net force, this here represents the net force, is equal to the forces acting on the ball. So right now the force acting on the ball is mass times gravity. So in this case I would have mass times gravity is a force going in this direction. There's no opposing force that I can put because we're in a closed system. As a result, I'm left with ma is equal to mg. So as you can see, both sides we have a m, so we can cancel out the m, and what we will be left with is that a is equal to g. So in other words, the acceleration of the ball is affected by gravity alone, so it's independent of mass. Mass in this case is just a coefficient of what's happening from a force point of view. So what is really the game changer in making this ball move is gravity. Therefore, gravity and mass are independent of each other. The mass does not affect the rate at which the ball falls as it relates to acceleration. Because remember, acceleration is a measure of a change in velocity. And again, in this situation, as you can see, there's no mass affecting this acceleration. Alright, so that's it. Thank you guys for watching. I hope you enjoyed and learned something. And have a happy studying.